Good afternoon, everybody. Thank you for coming and being with us here. I'm going to present the work that we have done around Reduce Acceleration. It's mostly work that we have done with Auburn University and how we took the levitated network merge and put it over RDMA and the results we got. Most of you guys know Mellanox and what we do. Our ICs, cables, software switches, and all of our portfolios. We connect everything over either InfiniBand FDR 56 gigabit per second or 40 gigabit Ethernet. And we are able to use it also to accelerate different applications. One of them is Hadoop. So for those who are not familiar with the framework, hopefully you guys do know the framework. Main two components. The first one is the file system, the HDFS portion of it, and the second one is the MapReduce. On top of it, there are today, I think, 17 different applications that leverage the framework and enable different types of analytics on top of Hadoop or databases. The main values are flexibility, mainly in the data types and how you put the data and extract it. Your scalability, so how you scale in terms of cluster size, and at the end of the day, it's how much it costs you to store or analyze 1 terabyte of data. When we did some analysis, what people look, when the people look on your Hadoop clusters, what their pain point, we find out that they have the same pain point that we have seen before. So bandwidth and latency. We want more, we want better, we just don't have it. So simple MapReduce, you have tons of files. You have somebody who wants to understand something about it and make money or solve some issue with it. A simple framework, nothing very important. We're coming from a marketing organization, so for example, if you want to do a target marketing or find the right pricing, you'll use MapReduce on all your databases. Most retailers today, this is where they are tapping in and looking all the data they have in the transactional, website, Twitter, blogs, and everything in order to target the right product at the right price. So different types of data. It can be structural, unstructural, pictures, text, whatever you think about, and you have to map it. So you take a bunch of computers and do some processing. So the data resides inside the nodes themselves. So there is no centralized storage as we are familiar with other places. Data resides inside the machines themselves, and you bring the compute on top of the data. And you get the mapping. The mapping is a key value information you take out of those information. The mapping scheme is done by the user itself. So I write a Java code, and I can map the data as I find it right for myself. And I can change that mapping time after time. I am not keeping the data mapped as a permanent results. I do the mapping, and then I have to do a reduction. For example, I want to do a regular count of how many titans do I have in my data. So I take the data which is mapped out and map output files that are written inside the hard drives at the machine themselves, take them to another machine, do the reduction, and get the summation. So that's the way MapReduce works. The only problem here is that there is a portion of data that has to move between the mapping and reduction. And this is a pain point. This is one of the most inefficient portion of the framework. And when we looked on the different portions of the framework to accelerate, we find out that that intermediate data, that A, is not written into HDFS file, and second, it creates a bottleneck on the network. So this is the framework. This is how it works. So the top line is the mappers. The mappers take the data and map it into their map output files. Then as the first mapper finishes its work, the data start to move inside the network into the reducer nodes. And that data information is starting to be merged and summed or reduced at the reduction phases. So the merge and shuffle, this is the movement of the data here, is done before even the first reduction started. So there's a serialization process inside the framework itself. Once again, not the most efficient one. The merge itself is a gory process for the machine themselves. What happens is that you have a certain amount of blocks of data that you have to read from each of the map output files, sum it, and put it either in your memory or write it into the disk. Once you do that, writing it into the disk, this is the most inefficient way, because then you write it down and you have to read it back once you have finished the next portion of merging of the data. In addition, most of the machines have a threshold on how many blocks you're going to merge every time. And every time you pass that threshold, you have to run the merging process. So the first block here in this example, the number of blocks is 3. Every time you pass the number of 3 different blocks, you have to run the merge process. And if the merge process of the file, or the size of the file, is bigger than the amount of memory you have to write that data into the disks of the reducer. So together with Auburn University, we came with a new algorithm. We don't read the whole map output files from the mappers into the reducers. We just take a portion of that output file. In most cases, it's only 1 kilobyte of the map output file. We know that the mapping process made sure that the information is sorted. So there is no inefficiency in that the reducer had to do the sorting again. The data came already sorted to the reducer. We know the priority of the data and how we have to merge it together. Using RDMA, we read the information directly from the mapper node into the reducer node without going through the disks. And everything is done on the intermediate data. That intermediate data, you don't see it on the HDFS cluster. It's data that it resides inside your compute nodes. And the process continues, and every time we bring another portion of the headers of the file, another kilobyte, and do the merging inside the memory of the reducer. So we don't have to read the information from the mapper node into the reducer node, read it back, and do the process. We read it directly from the mapper node. So the new process, as defined by the new pipeline, is all mappers have to complete the work. And the reason is that the map output file has to be sorted. And it is not sorted until the mappers have completed their work. So we put the framework into a process that's called all the mappers have to complete at least 95% of the work. And second is there is no speculative merge or reduction enabled in the framework. So what we see is that the cluster itself is working on the mapping. Once the mapping is completed, we can start the shuffling, the merging, and the reduction. Since we know now that the data is already sorted after the merge process, we can start immediately the reduction at the same time. So the merge, shuffle, and reduction start immediately after all the mappers are completed. The CPU itself, when the CPUs are working, they're doing either mapping or reduction. So there is no contention on resources on the machine itself. So we took the idea and developed a product. And the product is called UDA. It's open source. We are putting it on a Git or Google Code. We have not decided yet. Everybody can download it today from our website. Today we support Apache processes, so 1, 2, and 3, Apache versions. It's inside the trunk of 3.0, and it's going to be in 2.03, which should be released, I think, next week. With a small caveat, apparently we found a bug in the framework during that process, so we're trying to resolve the bug inside the Apache framework to support the third-party shuffling process. We have on our website patches for Cloudera CDH3, U4, and 5. and Hadoop Hortonworks HDP 1.1. From our process, it seems that it works on ConnectX-3 cards and our switches as well. In terms of the framework, since now all this shuffling and merge is done with a different shuffle provider, it's written in C. So we had to write a plugin into the framework, which is written in Java. So we use Jenny in order to integrate those capabilities inside the framework. So we have our RDMA process run in C code. The plug itself, the plug-in into the framework, it's only 5 if lines that we have put into the Java, so there's nothing different in that perspective. Mappers, there's no change in the mapping process, so if somebody is only doing mapping, it shouldn't affect his capabilities or the way he sees the data. But the merging of the data and the shuffling now is done in C, so it's done in a more efficient way. When we did some testing, we find out that we get around 50% reduction in execution time. So we took the vanilla, same hardware, same processes, same everything, and we see that we are able to run Terasort, and the guys who know Terasort probably will not be that happy. It's not the most representative process in the world for MapReduce, but it's somehow the most common one that people use today. What we see is mainly disk access goes down by 50%. And that's where most of the saving is done. CPU efficiency, so the CPU is doing less TCP/IP stack processing, and it's doing much more of the RDMA. So the efficiency on the framework itself goes up. And as I said, without the RDMA, you have a read and write, another read into the reducer. With the network-levitated merge and RDMA, you are able to do only one read from the map output file into the reducer node. So we look on the execution process, and what we see is that we have taken off all the reads that we did from the file buffers on the reducer side and made them over to the network. So there is almost half of the reads are gone, and you don't have to access the disk anymore. The reducer reads the information directly from the mapper disk if they're not residing on the same node. So it saves a lot of time and a lot of queries into the hard drives, which usually are the most inefficient component in the cluster. In addition, the file writes on the reduce side also goes down, and only the output HDFS file, which the actual reduction process, is written to the disk. So most of the capabilities or the acceleration comes from not accessing the disk drives in this process. We have another project we're actually running with Professor Panda on accelerating the file system itself. So since we find that the acceleration to the MapReduce was a more of the efficient way to do it, we look also on the file system, and I think Professor Panda will talk about it tomorrow on the project that he's doing around HDFS. We see that SSDs accelerate the process significantly. If you want to talk about the numbers tomorrow, that's going to be very exciting. So what we see is that when we talk to people about Hadoop, they tell us we need 1 gig. Well, we think that muffler shop stigma or romance time is over. If you do that, I don't know, people build clusters with nodes that have, it's a 2U box, 24 drives inside, Romley machines. Each box is $5,000, $6,000, and then they use the 1 gig and buy a Linksys switch at Fry's. And don't understand why they cannot scale, or they see issues with scalability of performance. So when you build your Hadoop cluster, you better look also on the network. And we see that once you open that bottleneck, it enables you to bring more capabilities and more. The cost of processing the data is cheaper at the end of the day. One more project that we have used is taking the framework itself and using only with SSDs. And what we have seen is that Hadoop flies when you do that. So we took a 40 gigabit Ethernet network card, vanilla. We didn't use any of the RDMA process acceleration. We didn't have it at that time finalized. And connected SSD, PCIe SSDs in the machines themselves. And we have seen that we are able to accelerate the whole framework by roughly, again, 50%. So we took a 1 terabyte TerraSort again with only 5 machines, 4 terabyte of PCIe SSDs inside the machines themselves, so it's a kind of an expensive box. And we were able to do the processing in less than 16 minutes. At that point, when we published it, it was a world record for that small size of machine. It's half a rack. Put it under your desk. And this is what we have seen. So we were able to cut the process execution time by more than half. Our products, if you look on the websites of the different distributors of Hadoop softwares, you'll see that our product is certified by Cloudera. We have good partnership with the different vendors like Hortonworks and MapR, who test drive their solutions on our clusters. We have excellent relationship with Greenplum. So when Greenplum releases their GPHD, they take all the new software and run it on a cluster that we have built together, a 1,000-node cluster. That cluster is open to the community to use, and it's free of charge. It's a 1,000-node running InfiniBand FDR. The cluster is located in Las Vegas. Everybody can just submit a request and run his Hadoop application on top of it. So I encourage you. It's an excellent machine. Dual sockets, 12 drives in each box, 48 gigabyte of memory. A really powerful machine. Doesn't cost you a dime to run it. Use it. It's for you guys. So to summarize, when you build a big data application, you'll still want to look on the performance, on your networking performance. So bandwidth, your latency, and your power efficiency. And also, if you want to scale, you'll find out it's easier to do it with InfiniBand, usually because you have an upper link that is easier and doesn't suffer from spanning tree type of issues. And that concludes my presentation.